In this video, we're going to do a walkthrough example of how to determine and sketch pictures of the sigma and pi framework in valence bond theory for CH2O. So what we need to start with is our Lewis structure. So you need to make sure that you feel really comfortable doing this, and if you want, right off the bat, this is a good place to pause the video, make sure and do a practice of drawing the Lewis structure for this, and then come back and see if you match up. Okay, so you should find that the Lewis structure for this is carbon with a double bond to oxygen, and then the two hydrogens attached to carbon. Now I have kind of already drawn my Lewis structure with an approximate Vesper picture, right? The steric number of carbon is 3. So this should be a 120-degree angle. It's trigonal planar. The piece that we have not yet dealt with when drawing our valence bond pictures is that the steric number of oxygen is also 3. It's just that with two lone pairs, we don't have anything to indicate when it comes to the Vesper geometry, but it will greatly affect the way that we draw the orbitals in our valence bond pictures. All right, so I've got a good Lewis structure. Now, for reasons that you will see when we get to the end of this example, I'm going to rotate my molecule in space before we do the valence bond treatment. You don't have to do this. It is entirely up to you, but what matters is that you have the molecule with an axis system and then use the appropriate orbitals for making the bonds based on how they're oriented in space. So we're going to use the axis system that we always do. And the way that I want to set this up is I'm going to put my carbon-oxygen bond here along the x-axis, and then I'm going to have my carbon-hydrogen bonds going back and coming out. So my entire molecule is in the xz plane, right? So this plane right here is the plane of my molecule. This is a terrible perspective way to show it, but this is what I mean. So when I go to make these bonds, and I think that doing this kind of analysis this way is a great way to set yourself up to have the right bonds pointing in the right directions, and it's a good way to organize your work to make sure that you get partial credit as you're going through. So let's see what we got here. First, on carbon, my steric number is 3. So I'm going to make sp2 hybrids, and I'll have a p orbital left over. For oxygen, my steric number is also 3. So I'm going to make sp2 hybrids, and I'll have a p orbital left over. And just a little bit of foreshadowing here, I've got a double bond between carbon and oxygen. So I need something that's going to give me sideways overlap for the pi bond, because in a double bond I have a sigma and a pi, and each one of these has a p orbital left over. So this is good. I think I'm going to be set up nicely for this. And then hydrogen, it just has the 1s orbital. It's not hybridized because we only have that one orbital to work with. All right. So the next question is which orbitals point at each other and overlap? Because this is what we need to make bonds. So my carbon-hydrogen bond, I need to make a sigma bond between carbon and hydrogen. So this is going to be a carbon sp2, hydrogen 1s sigma bond, and those bonds are in the xz plane. So my sp2 is going to be s plus px plus pz. So in order for the bonds to exist in that plane, I need to overlap orbitals that exist in that plane. So there are two of those. I'm only going to have to draw one example, but they're both going to be the same type. Now my carbon oxygen sigma is going to be a carbon sp2 and an oxygen sp2. All right. Now my carbon, I'm already making sp2s out of px and pz, and that carbon-oxygen sigma bond also exists in that plane. So on carbon, it's still going to be s plus px plus pz. And for oxygen, it's going to be the same. And that may not be completely obvious, but we'll come back and look at this in 1 second. We have one more bond to account for, which is my carbon-oxygen pi bond, because there are two bonds between carbon and oxygen. So the pi bond, and we'll draw the pictures to help you see this, has to be between two p atomic orbitals. So they're not hybrids, they're just the normal orbitals that we drew in a previous module. And so carbon, if I use px and pz to make hybrids, it's got to be the py. And the only p orbital that can overlap with a py orbital is another py orbital. Otherwise, you don't get any sideways overlap. So oxygen has to be a py in order to make that pi bond, which is why we know that the sigma bonds are going to be the s plus px plus pz. Now, I have one more thing. This accounts for all of the bonds, but oxygen also has lone pairs on it. So the oxygen lone pairs are going to be a part of our picture in the sigma framework. So just when you see later problems, it'll ask you to draw the sigma and pi separate. The lone pairs are considered part of the sigma framework. And so these oxygen lone pairs will be in the other sp2 hybrids on oxygen. So they're going to be oxygen lone pairs in oxygen sp2s. And we'll draw some good pictures of this. All right. Now, just another note. I know that this was in the one video. This is different from the book. Do not follow the instructions that are in any of the books. You should hybridize, which is what we've done here, all non-hydrogen atoms. So follow the instructions that are here and not what you see in the textbook. All right. So I have kind of a plan, right? I know what's making each bond. I know which direction it's pointed in. So let's draw some pictures. So my sigma framework, my carbon-hydrogen bond. Now the way that I've drawn these, I don't have a choice on putting one of them in the plane of the paper. You would be welcome to rotate your molecule if you wanted in order to do this. But because I've chosen to have my molecule rotated, I do need to draw this coming out of the screen. So I think it's a little easier to draw it coming out rather than going back. So this is the example that I'm going to draw. So my sp2, it's got a big lobe and a little lobe, and then that is overlapping with this hydrogen 1s. So this is my carbon sp2, hydrogen 1s, sigma bond. And then I'm going to say plus one more. And I don't need to draw it because it looks exactly the same. And I've indicated that there's one more that is in existence. Okay, so that's one sigma bond. I also have a carbon-oxygen single bond. So on my picture, I need the rest of the molecule. And then this sp2 points along this bond. And now this is going to be different because oxygen is creating its sigma bond also with an sp2. So I've got a big lobe for an sp2. There's oxygen for the center, and then it's got a little lobe here, right? I've got two sp2 orbitals that are pointing at each other with their big lobes, which will give me a lot of good constructive interference to make these bonds. And let me get my lone pairs in on oxygen. This is my carbon sp2, oxygen sp2 sigma bond. And I don't need to say plus anymore because there's only one. So this is the only bond like this in the molecule. Okay. The other thing in the sigma framework, all I have left is the lone pairs on oxygen. So this will be interesting. So I've got carbon with hydrogen going back, hydrogen coming out. I've got my double bond to oxygen, and I need to draw where my lone pairs are. And it's a little difficult, right? Because of how we draw our VSEPR pictures, we don't indicate going out or coming back for our lone pairs. But now that we have to draw an orbital on here, I need to make sure that orbital's pointed in the proper direction. So if I go back and check, my oxygen hybrids are in the XZ plane because I used PX and PZ to make these sp2s. So my oxygen lone pairs are going to be in oxygen sp2s. And I'm going to have one, so I'm going to do plus one more. And then just a star note here, it's going to be S plus PX plus PZ. So these orbitals have to point the same directions as the sp2 orbitals on carbon. So my lone pairs are coming out and going back behind the paper. So when you draw this, honestly, in this case, I'm going to draw the one going behind the paper so that it's abundantly clear that the lone pair is living in an orbital that is going back behind the paper. It's perpendicular to the screen, perpendicular to the paper, however you happen to be looking at this. It is not in the plane of the paper, and you will lose points if you draw it in the plane of the paper. Okay. So I'm trying to be very emphatic here because it's super important that these are pointed directionally, correctly, and consistently in your molecule. All right, that's everything in the sigma framework. The pi framework, it's just that one bond between carbon and oxygen. And so we've set up already, it's going to be a carbon py, oxygen py, pi bond. The way that my molecule is oriented, and I'm going to make this carbon-oxygen bond weirdly short for reasons you'll see in a minute. Right? Hydrogen going back, hydrogen coming out. Put my lone pairs on oxygen. So it's a py orbital on carbon, so I need both of those lobes the same size, and a py on oxygen, so both of those lobes the same size. And I need constructive interference. So if I shade the top of this p orbital on carbon, I need to shade the top of this p orbital on oxygen. Now sometimes if you draw these too far apart, you'll see that they draw little lines to connect them. That's just to show, right, the actual atoms are much, much closer in real life, so those orbitals are close enough to overlap. And you can see they're side by side, right? So we have them coming together. We have two places that they overlap in order to make this bond, and it is perpendicular to the plane of the actual molecule. All right, so that is CH2O. Let's do one other example really quickly, and we are going to do acetylene. So sketch, sigma, and pi framework. For it is C2H2, and it ends up being H, C, triple bond, C, H. All right, so I have sigma bonds, and I have one triple bond, so that's going to be one sigma and two pi bonds to deal with. If I put my molecule on my axis system, right, everything is along the x-axis for my sigma bonds. So on each carbon, so both carbons have a steric number of 2. So I'm going to make sp hybrids, and they're going to be s plus px because the sigma bonds point along the x-axis. So I can, for my sigma framework, draw this pretty quickly. So my carbon-hydrogen bond, I've got a carbon sp. And this is going to look weird, but we'll fill in the rest of my molecule. And that's overlapped with the hydrogen 1s. So this is my hydrogen 1s, carbon sp, sigma bond, plus one more, right? The one on the right-hand side looks exactly the same. And then I've got a carbon-carbon single bond, right? Because this was... both of my carbons are the same. So carbon sp overlapping with another carbon sp. Get the little lobes on those orbitals. And then each one of these carbons is still attached to a hydrogen. So carbon sp, sigma bond. And then that triple bond, the other two components of it are pi bonds. So this is the entirety of my sigma framework. And if I do my pi framework, let's take a second to figure out which p orbitals we need. So I used my px to make my sigma bonds. So I have py and pz on each carbon. So I will have one pi bond that's py overlapping with py, and then one pi bond that's pz overlapping with pz. And in this case, because they're made with different types of orbitals, you do have to draw them both. You can't just draw one pi bond and say plus one other, because they don't actually look exactly the same. So CPY, CPY, pi bond. So just do an axis system reminder, X, Y, Z. So the PY is in the plane of the paper pointing up and down. Get my carbons here, PY and PY. Tack my hydrogens on the end, and then these p orbitals need to be shaded such that it gives constructive interference. All right, then my second one, CPZ, CPZ. So carbon, carbon, make sure they're super close. I'm going to draw my hydrogen bonds, my bonds to hydrogen, let's say it that way, extremely long so I can put my orbitals in here. And then on this carbon, I have a PZ coming out and going back. On this carbon, PZ coming out and going back. And they need to be shaded to show constructive overlap.